You'll get it.
Live stream.
Oh, yeah.
Is it
Do you need
going?
help?
Okay, sweet. Did you use Discord first? Okay, sweet. Hello, everyone. Oh, God. So welcome to week 8, I think it is. This week, another talk. Who's keeping track anyway? So this week we have a collaboration about UQMARS. And ourselves, of course. And this week we have Miguel, who comes from UQMARS, but also this university just in general. Miguel is a PhD student here in the, is it engineering tech, like faculty?
ITW.
Yeah, it's ITW. Okay, sweet. PhD student here. He studies robotics. He does undergrad here as well. He's just going to talk to us about how robots see. So it's up on the slides. You've probably all seen it. That's why you're here. It's enthusiastic to hear about it. Anyway, Miguel has a cool talk. He's got some live demos, which will not break at all. And I'm keen to hear how it goes, so I won't talk for too long. We have one more thing. If you hadn't seen, afterwards we are going to the Red Room for burgers. So that is fully funded by UQCS. So afterwards, if you want a feed, you're not going anywhere, we'll all run over to the Red Room. We'll have burgers there waiting. But to have the burgers ready in advance, go to that link there, put your order in, and we'll put that in like halfway through or something and make sure the burgers are ready when we get there. So it'll give you like 30 seconds or something to copy that down. Cool. Sweet. Why is the game why not the school? Okay, so I'll hand this over to Miguel now. He's going to get started. Please give him a warm welcome.
Hi everyone, I'm Miguel. Just a bit of an introduction. I am, as you said, a graduate in electrical engineering. I just graduated a couple of years ago, and now I'm doing a PhD in neurorehabilitation robotics. So, yeah, technically still a first year. So let's just start off with what's on tonight. So I'm firstly going to start talking about what makes a robot. So it's just one interpretation. There's lots of different ways you can define what a robot is. And then we're going to look at how robots actually see. So that's how they acquire images. Next, we're going to be looking at image processing. You'll see a cool demo of that in a bit. Just a little bit about representing data. So you'll see that in a sec. Right now, I have with me a Kinect here, which you might recognize from Xbox One. This is used a lot in research, and I'll show you that as well. So let's start off with what makes a robot. Well, according to IEEE, a robot is an autonomous machine capable of sensing its environment, carrying out computations to make decisions, and performing actions. So TLDR, robot has to be able to sense, it has to be able to think, and it has to be able to act. So let's start in reverse order. So firstly, actuation. So a robot must be able to move and have the low-level control systems in order to do so. So for example, a robotic manipulator, so like one here on the left, it has to be able to move to any end position in any particular trajectory. Another application is requires that you are able to exert any amount of force on any other object. And on the right here, we have the Curiosity rover, so an example of a mobile rover. So that has to be able to move in any particular path with a particular velocity. Right. So that's actuation. We won't be focusing on that, but there's a few different talks based on that. I think Raggy might have done a talk. Did you do a talk?
Oh yeah.
Not yet. And then next we have thinking. So a robot has to be able to think for itself. It can't, I guess you could count a robot as a robot if it just follows instructions, but it helps if the robot can make decisions based on its environment. So yeah, on the low level, it's not really, like, thinking is basically just maths. And then finally, a robot has to interact with its environment. So what good is a robot if it can't actually interact with the real world? Yeah, and it needs to be able to sense the environment and adapt to the information, adapt to the environment using the information that it's gained. So there's a few different ways it can interact with the environment. A lot of common sensors are torque sensors, distance sensors, so like ultrasonic, IR, LiDAR, time of flight, as well as inertial measurement units, so things that incorporate acceleration, as well as gyroscopes. Then also you have positioning sensors, so like GPS, magnetometers. And then finally we have camera sensors. So this is what we're going to be focusing on today. So yeah, we'll be looking at camera sensors. So if you see this, there's a little camera there. It also has an IR projector, and that allows it to project the IR light out and receive it back, and that's called a time of flight sensor. There's a lot of really cool applications based on these sensors, and we can use those to gather meaningful information from the signals that we get. So let's look at a recipe for how to see. So step one, stuff there. Oh, there's an animation. I knew that. So firstly, we need to convert the energy from the photons into electrical energy. So in some sort of circuit for each pixel on the sensor. So if you imagine a camera, it's got like a whole array of different sensors that are all capturing different light levels, potentially with different filters if you're using RGB. And of course, you need to sift the photons through the filters as needed. Step two, you actually need to get a signal from that, right? You need to convert the electricity that you have into some sort of readable signal. And this is usually done through the process of sampling and quantization, which is essentially cutting up and organizing your signal into separate bins or separate bowls. And we do this in order to make processing a lot easier down the line. I don't know if you guys have done any cooking, but the French call it mise en place. So step three, so you got your signal, you know all the values for the pixels. Now what you need to do is organize that into some sort of array, right? And that array has to be represented by a number value. So yeah, this is sort of digitizing your signal and actually storing it in some sort of computer. And then finally, once you have the image stored on the computer, you can add your finishing touches. So that is to process the signal digitally to get rid of any unwanted noise and to just make the image in general more useful. So this also includes things like encoding. So you don't want the image to take up a whole lot of space in your computer. So instead, you can compress it in any way you want. Yeah. So once you got the image, what can you do with it? So there's a couple of things you can do. Firstly, data collection. If you just want to store your images to be used later, you can do that. You can also process your images in real time. This is something that's quite difficult to do, especially with very complicated algorithms. like these cameras are running at like 30 frames per second, and having to process each frame individually is can be difficult to do. Next, machine learning. So, of course, if you're trying to train something like a neural network, you need a lot of images for that. Right? And then finally, computer vision. So that's something we'll be talking about, and that's to do with gaining more information from the images in a way that is similar to how a human would process. So humans able to get lots of information just from sight, and that's sort of based on intuition, and it's complicated, and we'll see that in a sec. So yeah, how do we do this? Well, a common way to do that is through image processing. So image processing is essentially just convolutions and algorithms. It's applying filters, doing things like thresholding. And you can do that through a few different libraries. In this case, the ones that I use mostly are OpenCV, and then Pillows also use a lot in Python. So yeah, one way is, so I mentioned filtering before. One common way to filter is through using kernels. So has anyone seen what a kernel is before? People in the course that I'm tutoring, I'm sure you've seen a kernel. But essentially, it's a way to apply a filter to each portion of the image. And I'll show you a bit of a demo for a few of these filters in a sec. So yeah, let's start the demo, and I'll just check that you can see. Give me one sec. These work? Don't crash? Anything showing up? Let's see. Cool. All right. So can you see this here? Oh, it's got an infinity effect. I'll show you my code as well. Don't be scared. It's just it's just Python. It's fine. So there we go. There it is. So what I'm doing here is essentially I'm applying a few different filters. So at the moment, this is the default filter. So nothing at the moment is being applied to it. But next, does that work? Notice anything different? It's a bit blurry. Yeah. So what I've done is I've applied what's called a Gaussian filter. And that works by essentially taking this. You can sort of think of it as like another image. This looks like sort of a bump, right? And that bump is used to essentially blur the image as it goes across. Right. If I go to my next one, slightly more blurry. That's different, and that's using a 5x5. Right. Let's go do some more funky ones in a sec. Here we go. So this is the Sobel filter. And what the Sobel filter is used for, usually, is for edge detection. So you can see it can really get the edges of pretty much anything I put in front of it. Right? And it does that by essentially taking the difference between neighboring pixels. So if there's no difference between neighboring pixels, you'll get gray. If there's like a positive, like an edge there, you'll get a high or really low value, which is represented by either black or white here. Well, this is RGB, so it's a bit different. So yeah, this is the X, so that'll get any changes in one direction, and then this is the Y. Cool. I got some weird ones as well. That's a bit cursed. So this is what the dilation filter. And what it does is it takes a neighborhood, in this case it's a circular neighborhood, and it finds the brightest pixel in that, and it replaces that pixel with the brightest pixel. So if I introduce anything that's like what's something that's bright? This is bright. It'll sort of dominate anything. Sort of like blend with me. In contrast, this is the erosion filter, which does the opposite. Instead of taking maximum, this is take the minimum, right? So yeah, let's have a look at the code. I know you guys love code. Yeah, so this is the dilation code and the erosion code. Essentially, this is taking a neighborhood and then replacing it with the maximum value in that region here.
You don't have to look at it.
Oh, yeah. Maybe. Can I?
Yeah.
There you go. Oh, let's.
Don't get really out.
I'll just close this. Yeah. So this is pretty slow, you can see, because I'm not really optimizing this code, but it seems to be running fast. And in contrast, I'm also using this filter operation in OpenCV, which allows me to apply these kernels here. Yeah. So, any questions about this? Do you want me to go through them again? I can go through them again. Just the last one, yeah. Going to the start, other. Yeah. So yeah, blurring, edge detection, whatever that. All right, that's enough of that demo. Let's go back to the presentation. Is this, yeah, cool. All right, so let's go back a bit. So we've collected our data. In this case, we've been collecting images, but there's a lot of different data types of data you can collect. So I guess when you're trying to represent data, you have to ask yourself, what are you trying to represent? So one thing is representing 3D objects. So there's a few different ways you can represent that. You can also represent depth data in a couple of different ways. And there's of course like time series data. So that's used for like robotics if you want to track the positions or torques by each joint or motor. Cool. So yeah, I'll show you a point cloud. Oh, that sounds weird. So here we go. That's me. Definitely didn't record this today. Yeah. So that's using this Kinect thing, and that's extremely useful for representing some sort of surface. But of course, that you can convert that into other forms, right? It's all, I guess, representing the same information, but different representations. Can I go to the next slide? No. There we go. So yeah, one type of representation is, of course, images. So images are really useful because it's literally just like a two-dimensional array, and you can do lots of fast math with that. In particular, using it for things like convolutional neural networks. Yeah. So yeah, now we'll have a look at different ways to represent 3D objects. So yeah, so we got some point clouds. So this one, that dinosaur there, is actually a point cloud, but it's just very high resolution, so you can't see the points. Over here, I've rendered a mesh of a dinosaur, and that's rendered in OpenGL. We can see, I don't know if you guys can see this, but here you can see the individual triangles that make up the dinosaur. Right? And that is just one way you can represent a closed surface. In addition, you have things like voxel plots. So one example is, yeah, the same dinosaur, but rendered in Minecraft. Yeah, that was fun. So the voxel plot is stored in an array. So it's like a three-dimensional array where you assign some value to each like cube in that array. Right. So imagine getting like some rectangular prism, cutting it up into cubes, and then you assign some sort of data for some sort of value for each point or for each cube in that array.
What's a mesh?
A mesh? Okay. I'll go through these a bit more in detail. So a mesh is essentially a list of vertices, edges, and faces that make up some sort of closed object. Usually it's a closed object. And one common way to represent meshes is using triangles. So that's literally defining 3 different points that make up a face, and then you do that for every single face. So you can imagine that takes up a lot of data, for example, that. And even processing that would take quite a lot of computation too. So we can see there's lots of different advantages to them. So point clouds, the advantage of that is that you just have a list of points, and then you can do the same operation to the points, and you don't really need to know the relationship between neighboring points. Right? That's sort of just a list. But that's also a disadvantage because there's no sense of nearest point. Yeah, so next let's have a look at an RGB camera. So that's what this is. So you can see from here we've got your RGB values and then also the depth values. And you can combine them together to make some sort of cloud or some 3D representation given just, an image and a depth map. So, one of the really well-known depth cameras, or at least consumer-level depth cameras, is the Kinect. So you can see here, this is the old Kinect, made for Xbox 360, and this works through sort of triangulation. It has one emitter, which basically outputs these dots. It's like a dot projection. And those dots can't be seen by the human eye because they are infrared. But of course, the actual Kinect can tell where they are. And from that, you can triangulate how far a certain point is. Yeah, so Kinect V1 was like the first version of the Kinect. It could only output a 480p video stream, and the depth was also 480p. The one that I have here today is the Kinect V2, which uses a slightly different method for getting the depth. This uses a time of flight sensor, which you might see in other things like ultrasonic sensors. They're all time of flight. Yeah, the advantage of this is that you can output a full HD image, which is obviously very useful for computer vision. So I'll show you a few of the applications of this Kinect. Although it did flop in gaming, it was a bit of a gimmick. It's used a lot in among researchers because it's really cheap, and it's pretty accurate actually. So yeah, what we got here on the left is the Kinova Novo robot. That's a robot that I worked on during my thesis, and there's an undergraduate student now working on that. Yeah, and so essentially we use this robot to interact with subjects for upper limb movement assessment. So moving your arms around and recording that. And the advantage is that you're allowed to interact with the subject in real time. It gives sight to the robot. Oh yeah, his name's Craig, he's got a tie. But yeah, we can also use it just for general movement assessment without the robot. We have a couple of Kinects that are used to record movements of subjects as well. Cool, so let's go to the next demo. It should be fun. Oh. Okay, oh, that's back. How do I close this? Can I close this? I'm a little frightened. Oh, that's... we need to close. There we go. Is that gone? Okay, cool. Give me a sec while I open the other one. There we go. So, what we got here is the output from this Kinect camera. Can I grab a volunteer who would like to come up? Do you want to come? I mean, it's not. It's fun, but it's just. Now here. You can come closer. Actually, it would be better if you come a bit closer. Try just like this, like this. Yeah. So we got here. What we got here is what the camera is actually seeing. So bottom left, you have the regular RGB stream. And then the top left, you have an infrared sensor. So you can see, it's a bit hard to, if you stand slightly back and then stare at it, you can see your eyes. Yeah, there we go. Yeah. I think who's going to see the front? Let's see someone's eyes. Looks terrifying. There we go. Yeah, essentially it's outputting an IR light, and then it's receiving it back, and then timing how long it takes. And then from these two separate cameras, it's able to figure out what the depth is, which is what that bottom right image is. So if you move closer, you'll see the depth will change, and like stick out your arm maybe. Yeah, if you get too close, it's a bit hard to see, but you can see there's like a slight difference. Yeah, see, like if you stick your arm out now, you can see that's darker because you're closer. And then the further away you go, the lighter it becomes. Yeah. And then, yeah, you might notice there's one other image in the top right there. And that's called the registered image. And what that is essentially a mapping between this RGB image and that depth image. And we need to actually create a mapping, and it's not exactly trivial. And that's because these are actually offset from one another. So right now I'm blocking the RGB camera, and you can still see the depth image. And then now I'm blocking the depth image, but you can still see RGB. Right, so that's a mismatch between these two, and it needs to like correct that essentially. Especially if you want to represent it as a color depth map. Sorry, a color point cloud, which is what I showed you before.
Am I still necessary?
Sorry?
Am I still necessary?
Yeah. Give it a sec. So, yeah, you can see there's a few issues with this as well, and that's just an issue with the time of flight sensor. You get a bit of noise, but again, you can use things like image processing to filter that out.
Yeah.
Is that a question?
Yeah. Why does it go black instead of white the area of time? Like the time of light swap?
Oh, I mean, it's an arbitrary choice. You could set it to any value.
Okay.
But anything that it doesn't know what the depth is, it'll just assign to 0.
Okay.
Yeah. Because you can't really get 0 distance away from this.
Yeah.
Yeah. So it just makes it.
Is it meant to be like the? There's like a green
Oh, yeah.
highlight.
That's weird. I think no, that's a projector.
That's the projection.
That's a projector. Yeah. All right, cool. Can we get a round of applause?
Oh, thanks.
All right, back to the presentation. You see it? Cool. So, what now? Let's move on to computer vision. So we just got all the data, so using IR sensor, cameras, whatever. Now what do we do with it? Well, we can use computer vision, and there's a few different approaches to it. And there's like sort of a divide between your like traditional approaches, which is using what I showed you before with the image processing and kernels, as well as the compared to the deep learning approaches, which is what they're using now. But then they're both used to solve like very similar problems. So a few of those problems include segmentation, which is essentially figuring out what object each pixel belongs to. So if you look at the room, you can tell where in your vision is a person and where in the vision is a chair, right? You're able to segment that yourself. But it's, of course, not very trivial for a computer to do. This also is used a lot if you do like photo editing. It's useful for just like creating a mask of the subject. So that's sort of segmentation. Yeah, and a couple of other ones, you have classification, which is being able to tell what you're looking at, right? So if I showed you a dog, you would know that it's a dog. But like if you told a computer to tell you it's a dog, it's a bit harder, right? And that's where you have some advantages of different approaches. You have detection, so that's being able to tell where a certain object is. So for example, if I said, here's a picture of a car, where's the license plate? You'd be able to figure that out using computer vision. And the final two, we have facial recognition. So I'm sure you're all familiar with that. And then, of course, pose estimation. So pose estimation is a lot what I do, which is being able to find the locations of your different like joints just from an image, and being able to work out where you are in space. So yeah. So traditional computer vision relies a lot on I guess feature extraction. So that's knowing things like edges. So edges are a common way to do feature extraction. So if I wanted to detect like where the whiteboard is, I'd probably detect where these edges are, and then go from there. What else we got? We got thresholding. So thresholding is basically being able to pick out a certain color or a certain shade just based on the image. Yeah, a few other things. You got energy-based optimization. So how do I explain that? Sounds a bit tricky. Imagine you have an image, and then it's a grayscale image, and you render it as like a depth map, and you place like a rubber band on it. By putting that rubber band is going to like settle to some position, right? And that will be based on the energy of the rubber band. So its tension, gravity, all that stuff. It'll settle to a certain point, and that rubber band will give you like a line around. It'll give you a path around that image. So that's one example of energy-based optimization. I'm not sure if I explained that very well. But that's okay. That's used for segmentation as well. Like if you want to get an edge around something without using regular edge detection methods, you would use an energy-based method.
That's like a Dijkstra's algorithm, but they extended it.
Yeah, it's very similar to Dijkstra's algorithm. So that's based on some sort of like cost function, right? So it's the same with energy-based optimization. You have some like function which you want to minimize, right, with respect to some sort of path. Yeah, and finally you have frequency domain filtering. So while it is really good to be able to do techniques just based on what you see, some techniques you need to look at a different domain. So looking at the frequency representation of the image, which don't worry about that right now. So let's move on to deep learning approaches. So yeah, one of the advantages is that this can be really accurate, but however, it does rely on a very large data set. Right? You need lots of training in order to get your network to perform well. So an example of that is the MNIST handwritten digit database. So that's a set of 60,000 28 by 28 grayscale images, and that's literally just for creating networks to either recognize handwritten digits or even generating them. Yeah. So the reason why we're seeing a lot of these now is because we're sort of getting better with processing power. We have a lot of GPUs which are very good at doing parallel processing, and that's something that you can use to your advantage when you're doing deep learning. I'm sure you've seen there's a few different frameworks that you can use in order to build models for these. So TensorFlow, as well as PyTorch, and you'll use those in like some courses. So yeah, one of the other disadvantages of using deep learning is that once you actually get the model, it's not very intuitive to understand the model. It's it's not very interpretable. So if you have a look at this, sorry, before we do that, I'm going to jump to this slide. Order. So yeah, one way of doing, one example of a neural network is convolutional neural network. So this uses kernels like before, except the kernels are actually trainable parameters. Right, so you can actually find the best set of kernels, which would give you a certain output based on, like an expected output based on any input. Yeah, so essentially if you give it, an example of this is like you give it a robot and it'll tell you if it's a robot or not, right? So if you give it, you would expect that if you give it something that's not a robot, it would give you a 0. And if you gave it a robot, it would give you 1. But then in order to do that, you go through all of these different like computations, right? So yeah, going back, these are the kernels that you get from training. I think this one's, I don't remember which, yeah, the MNIST database. So you can see these are the different weights and the different kernels that you get. And they don't really look like digits at all. It's sort of like random. And that sort of goes to show that you can't interpret what you're given after you train a neural network. It doesn't really, you can't really use that for anything else. It doesn't give you an understanding of like the underlying like processing for that for whatever problem you have, which of course isn't very useful. Like if we want to design new techniques, we need to be able to understand those traditional methods. Yeah. I also have another demo. Last demo. I'm sorry. So let's do this again. How are we going for time? Oh, cool. Good. Where is
Yeah.
Please work. Cool. Can you see this? It's a bit tiny. Wait, what? What happened? Where'd you go? So tiny. It's tiny. It's fine. Anyway, you can see that I'm running this on my laptop right now. And it's essentially a face blurring algorithm. But of course, in order to blur my face, I need to know where it is. Yeah, this method here is using like a cascade, which is complicated, but it uses a traditional computer vision technique to actually find where my face is. And you can see it's not very accurate, especially when I turn around. Yeah. You can get more accurate face detection with a deep learning model, of course. I did want to show you another thing that I used, that I'm using currently in my PhD, but it doesn't run on this computer, sadly. But I might show you the GitHub page for that afterwards. Yeah. Wonder if it can get anyone in the audience. Maybe. Let's see. Anyone want to come up? Oh. No, it's too far away. It's too blurred. No. All right. Let's go back. Any questions? What am I doing in my PhD? Oh, I will talk to you after. But okay, essentially I'm doing upper limb movement assessment for stroke patients. So like recording their movement and seeing if we can use that to design better therapy methods. It's long. Sorry?
What's the traditional computer vision technique you're using to find the face?
It's like I think it's using hard cascades.
hard feature.
It's like it's a
feature set.
sorry.
That's like hard handcrafted feature.
But essentially what this is doing is it's searching for my face based on certain features, and then if that passes some test, it'll keep searching for my face to get a more precise location, and then that's of course in a cascade, and then it finally decides whether what it's seeing is a face or not. Yeah. This is anonymous enough, yeah. Yeah, I don't think this is very good for protecting. Yeah, you wouldn't use this for witness protection. Yeah. All right, let's go back. Cool. So let's go on to. Sorry, this is fun, great. So looking back at robots, right? I'm going to talk a little bit about SLAM. So what is SLAM? Well, it's simultaneous localization and mapping. But what does that mean? All right. I think the best way to understand what that means is to do a thought experiment. So essentially, you try to put yourself into the shoes of a robot, metaphorically, but using your own intuition. So let's say you're put into a room and you've never seen it before, you don't know what the layout is, and your eyes are closed and you're not allowed to move. All right, so you know absolutely nothing about the room. You don't know where you are in the room, you don't know what the room looks like, you don't know where any objects are. And then you're told you have to find 5 different objects in the room. You can't touch them, but you just have to find where they are. And then suddenly, let's say you're able to open your eyes. So as soon as you open your eyes, you can see half of the room, or you can see one side of the room. And then from that, you can build sort of a mental map of where everything is in the room, based on what you're seeing at that present moment. And then next, you're allowed to sort of move around, you're allowed to turn your head, and then from that, you can see a little bit more of the room. But then you're still staying still, right? So you know where you are at least. And then you're asked, okay, you have to find 5 different objects in 5 minutes. And then you're allowed to move as well. So what do? You move around the room, right? But then once you've moved, right, you're in a different position now. So you can't really attribute, it's a bit difficult to map what you just saw before to what you're seeing now, right? Because it's a different image. And then part of SLAM is essentially figuring out what the correspondences are between those 2 different images, right? Does that sort of make sense so far? Yep. And then next, of course, you're allowed to move around. So you turn like 180 degrees, right? Just because I've turned around now doesn't mean that you guys have stopped existing. I know that. But the robot needs to take that into account, right? It needs to have some sort of object permanence, right? In addition, if things are occluded, so if something's like hiding under the desk, I need to know what that is. So I need to move around and try to incorporate that into my mental map. So a few other quirks of SLAM, so or just image processing and computer vision in general. So you might notice things get smaller when they're further away. You as a human know that. You know that a chair that far away isn't just really tiny, it's just far away, right? But then how do you incorporate that? Well, you can use other sensors. So for humans who have 2 good eyes, you can use your vision as sort of binocular vision, and that allows you to estimate depth of what you're seeing. And that also gives you more information about the room. And then, if you're good enough at remembering where everything is, you can close your eyes and then pick out what those 5 different objects are without ever opening your eyes again, right? Or at least maybe a robot could do that. So yeah, that's essentially SLAM. Oh, of course, it is a little bit more complicated than that. The main thing is that you're trying to localize where you are, so figuring out what position you are in space, and also developing a mental map of where everything else is in space. Any questions? Yes.
So slam averages are better than G rolls at object reference.
2-year-old. Yeah, yeah. I mean, if you put like a thing in a box, a 2-year-old would be like, I don't know what this is. It's gone. Yeah, I wish I was good. That's another story. Yeah, so usually with Flam, I just explained it intuitively, but we use things like column filters in order to, I guess, create that map, in order to get the right information, everything. So I guess column filters are all about like reweighting your sensors, and I'll show that a bit. But essentially, it's all about like updating your. It's about estimating positions and updating your priors with new information. At least column filters are. So that's like creating some sort of model in your head of how things behave, predicting what that model is going to do as you go forward in time, and then updating that with your new information. So yeah, I'll talk a little bit about that. Yeah, so everyone has, I guess, slightly different sensors and body mechanics, right? So it's not really good to rely on just one of those inputs. Like imagine if all you could do was just see things, right? You would fall around everywhere. But what your body does is it incorporates all of these different sensors into something that's actually useful, right? So let's go with another example. So imagine you're walking, you're like me and you need glasses. Where are my glasses? And then suddenly your glasses fall off, right? And okay, imagine you've got worse vision than me. And yeah, so your glasses fall off, right? Now you can't see because it's blurry. Would you keep on relying on your sense of sight, or would you then, I guess, try to incorporate other senses in? Well, obviously, you know, you probably try to reach around, right? Use your other senses, and that's what a column filter does. So based on, I guess, the quality of information you're getting from each of the signals, it'll then attribute more of that estimation to one sense rather than the other. Does that sort of make sense? So if I know that my vision's bad, because it's noisy or whatever, or if it's blurry, I'll try to incorporate like proprioception or my sense of touch. Yeah. So another one is imagine that you're playing a video game in virtual reality. How many of you guys have tried VR before? Most of you, okay. So it's really weird when you put it on, right? Because like, especially if you're moving in the game and you're not moving in real life, it feels weird to move, doesn't it? Because you're not actually feeling that sense of acceleration in real life. But eventually you get used to it, and getting used to it is, in a sense, recalculating your gains for each of those senses. And eventually it feels pretty natural to like move around in VR chat. Yeah, so what else? So these are sort of the problems that robots face when they're trying to handle like a whole myriad of signals given to it. And that's, yeah, essentially extracting information from all of that raw data, like fusing all the different sensor information. Cool. Yeah, fun math slide. Yeah, this is the maths for what's called an extended column filter, so EKF. But it works on like Bayesian principles. So you see a few different variables here. You got X, which is your estimate of your state. You have P, which is your covariance matrix. Don't worry about that too much, but you do use it a lot. And you have your ZK. So that ZK is your measurement. So that's what you're actually sensing. And so I'll sort of explain what this is. So the very first step for a column filter is to get your predicted or your estimated state from your previous iteration. and then like project that to your new state. So that's like stepping forward in time. And that's based on some nonlinear function f. And then next you've got to do the same thing for your covariance. Yeah, so that's your prediction step. Next, what you're doing is you're updating your information, updating your estimation from new information. And then you do that by essentially taking the difference between zk, which is your observation, and your h of x of k, which is essentially a mapping between your state and your output, which should be similar to your observation. And then the next few steps are essentially calculating what's called the Kalman gain. In the case of a linear system, this is actually the optimal gain that you can do to calculate in order to estimate your system very well. Right? Essentially, you need to calculate that using this formula, and then update what your prediction was based on that. So that's this step here. And then the same thing for your covariance. And yeah, that's Kalman filters. Are there any questions about this? Yeah. If you want to get anything from this, it's that there's like two main steps. There's prediction. So where do I predict that I will be based on my current information? So if I know I'm moving forward, right, I predict that based on my internal model of my body that I will keep moving forward, right? And then of course I can see from my observation, oh, I'm looking at my feet are moving forward, so I must also be moving forward. And then it's of course updating what my internal model is from. And yeah, that's Kalman filters. Yeah, any questions? Yes.
How do you know your next prediction is going to be better?
Sorry?
How do you know your next prediction?
It's going to be better. It is, yeah. So if we go back here, there's two things that you have to take into account. So that's Q and R, and that represents your how much noise you have in your signal. Right. Essentially, if you have a lot of noise in your, if you know that there's a lot of noise in your observation, then you'll attribute your next state more from your prediction rather than your observation, right? But if you know that you have zero noise in your observation, you can you can basically update your estimate to be that observation. So essentially that'll change what the K value is. If K is 0, that means that your prediction was perfect, right? But if K is very close to the identity matrix, then you'll get that your observation will be equal to, sorry, that your next state will be equal to your observation. I don't know, there's a way to like mathematically prove that this is optimal, at least for systems. Yeah. Yeah, and that's sort of it for this talk. Yeah, so to reiterate, we went through different ways to process images, we went through different representations. I showed you some cool demos.
I was just also curious, what's the model that you use to make the further prediction? Is it like a kinematic model?
The F.
Yeah.
So this is a general like, extended Kalman filter, but then that model will be dependent on whatever system your model is, right? Sorry? Yeah, it's like a plan. Yeah. Control stuff. Yeah. You know. Any questions? Any other questions? Yeah.
I was just wondering with that edge detection filter you're showing us, you're
Yes.
going to go one direction at a time. Can
Yes.
you do both?
Yes, you can do both. So Let me go back. So essentially, these are two different Sobel kernels, and that gives you the gradient in two different directions, right? So one will tell you the gradient in x direction, and one will give you the y direction, and you can actually take those two to be sort of like a vector, right? So it'll tell you how steep it is in this direction and that direction, like combined. And of course, if you take the magnitude of that vector, that'll give you, that'll tell you whether there's an edge at all. Yeah. And it also tells you the direction of that edge, which is also pretty useful. That Sobel kernel is one method of edge detection, but there's lots of other ones that you can use that are generally, I guess, more accurate. Right? They'll give you a better representation of the edges of the image rather than these. But this is like the prototypical example. Yes.
If you want to learn with content, what course will you do?
Oh, that is a very good question. So, for those of you who are studying engineering, in particular electrical mechatronics, you can learn a lot of this content in a course called Elect 4630. I know a lot of you are taking it now, so and that's the computer vision course. Are there any other courses you learned in?
The 20, there's a course called pattern recognition.
Oh yeah. So yeah, there's a course at UQ. There's a few different courses, but there's pattern recognition. Can't remember the course code. It's like comp something. What else can you learn this in? Oh yeah. So if you're in mechatronics, you'll probably have to take a few different control courses. And those control courses, well, the second one at least, will teach you a lot about Kalman filtering. Because you learn a lot about state estimation in that course. So that's meta 6203, I think. Yes.
Do you think CS majors could take the elect course?
The weird things that I don't know if it's offered. If you have a spare elective, maybe it does require like a couple of prereqs. Kind of just like if you know like signals and systems kind of thing. But that's sort of stuff you can learn on your own. Yeah, I'm not sure about CS majors. I know this is like UP, yeah. And I kind of wish this was also offered. It's more generalized. But yeah, yes.
More pose estimation.
Pose estimation. I don't think so. I mean, it's kind of niche. But if you do want to have a look at pose estimation, there's this really cool library. So I was going to show you the. Sorry, I know we're running over time, but I'll show you this. Cool. So this is called OpenPose. This is what I use, and that allows you to essentially detect, different joints. And this is able to do it in real time. Like I was able to run this. Of course, it's a good graphics card. But I was able to run this at like almost 30 frames per second. Yeah. And it's able to do the good thing about this library in particular is that it doesn't actually matter how many people there are in the image. It'll process it at the same speed. So it's able to do things like that, probably in real time as well. Yeah. So this is called OpenPose if you're curious. There's a few other similar pose estimation libraries, but this is the one that I'm using. Anything else?
Cool. Well, maybe give Miguel a round of applause. We have a mug. We give mugs to all of our speakers. You get another one. Do you have one?
I don't have a mug yet.
You should have an old one by now. We'll get you one. Anyway, so thank you for the talk.
Thank you.
We're heading to the red room in a second. So I suppose if you have any questions from Miguel, you come to the red room.
Yeah.
Yeah, good. So ask Miguel questions there. I'm offering him up to questions, but answer them. So yeah, we're about to head to the red room. We'll help tackle all of this.